This is part two of our Coding Essentials for Scientific Computing Applications. The date is 29 August. We were here where we talked about the three musketeers of coding statements: sequence statements, decision statements, and repetition statements. So these are some of the essential components when you're coding. Before we get into our logic exercise and prove that 2 equals 1, we want to review a little further to cover a sensible process for developing coding skills, and we mentioned a secret sauce, the secret sauce. So let's go ahead and take this up from here. So more time and preparation up front is the key to making the development of your coding skills a much easier and much more intuitive process. We don't emphasize this enough as computer science professionals, and that's kind of a shame. But basically, there are some simple tools that really help a great deal. So the first tool is called an IPO table. That stands for input, process, and output. And what I'll do here is switch to this IPO table. So here you see a simple table, and it's not very complicated. We have 3 columns, one for inputs, one for process, and one for outputs. And what we do is simply put basic information about what we know the input data needs to be. And then we think about the things we want as results. What are the outputs? And then the process in the middle becomes more intuitive. So if you think first about, well, actually, um, it's always good to start with the end result first. So that's kind of counterintuitive. Think about the things that you want to come out of the software, and that helps you that's what cues you into or gives you a hint about what you need for the inputs, right? So if you want information about social security numbers and where they live, I'm just talking about like a simple application that helps us identify social security numbers based on geographic location. You would say, well, I want to know which social security numbers live in which parts of the country, right? So talking about GIS locations and social security numbers, that those would be the end results in the report that comes out. So obviously there has to be an input that feeds in GIS data and social security numbers. In any case, the table helps you think about the inputs that are needed, the outputs or results that are going to be generated, and then there's this middle column that talks about process. And what you see here is a partially completed IPO table. Now in the lower portion of the IPO table, once you have the basic information here, you can start identifying the kinds of variables that you need in order to make those things happen. Oftentimes, this is one area that really throws a lot of students. Many times when you're processing data, there are temporary results. So you have to have variables for conditions and also for temporary results when the process is running, right? So you work part of the calculation or computation, you get an interim result, you have to store that somewhere before you can do something else with it or add to it or process it, analyze it, right? So there are interim variables, and then there are variables that you need in order to be able to create the output, whether that's a printed chart or a display on a video screen. It all depends on what you're doing for outputs. We're going to talk more about variable names in just a minute, but here you see that we have to have a name And down here, we've started to create variables and initial values for the variables, right? This lower section again is where you can take the information from up here, and then you can start thinking about what kind of variables you need down there. Let's return now to, well, let's see, there we go. So we saw an IPO table. The next thing that you do after the IPO table is created is build a flowchart. So what you saw before in the IPO table was like the beginnings of a registration app. And so a lot of times when you're looking at an input and an output and a process interest, a lot of people get the wrong idea about a flowchart. They say, well, we're going to have this huge object called input, and then we're going to have process and output. It's not three big chunks on the screen with two lines in between. The flowchart is more detailed, and so it helps you sort of work back and forth. When you have the IPO table, it becomes more natural to think about how the flow of actions are when you're building an app. Let's take a look at the IPO table again. So as I'm getting input, there's process, and I may get another round of input and then more process and then another round of input and more process. And so as we go to the flow chart, you'll see that that's reflected in the steps of the flow chart. It's always good to work with graphics, right? And so if you have a beginning and then you say display a message, welcome new user, let's get registered, and then display the next message, please enter your name. Then you capture input, right? This helps you understand what's happening along the way, especially when there are decision points or breaks where you can answer true or false, yes or no, and then a whole series of other steps are calculated. After you have your flow chart, after you have the flow chart created, the final step is to build out something called pseudocode. So you want to use the language side of your brain and think in plain English. We're not worried about the coding elements at this point. We just want to make simple statements about each of the steps, and we want to include some of those elements from the IPO table and from the flow chart. And at that point, once the pseudocode, these are statements that are created using plain English and not really code. But once you build the pseudocode and you get into the programming environment, you'll see if the pseudocode is created well enough, the code writes itself. So let's take a look at pseudocode. So here's the same example of a registration screen. I'm going to build some variables, and I'm going to make sure that those variable labels or names reflect their purpose and the data type. We'll talk about that more in a minute. But essentially, you see here, when you write out in plain English what you have based on the IPO table and the flow chart, it starts to come together. We're going to begin the program, and it says display, welcome new user, let's get registered. And this is going to help when it comes down to actually grinding out those coding statements. Let's see, where are we? Oh yeah. Now, the secret sauce is something you've started to, if you've been paying attention, you've noticed the variable names have a particular format. And if you want to make coding easy, this is one thing that, again, is underemphasized. So The basic tools to get organized, we don't talk about that a lot. People skip steps, they take shortcuts, and then they can't figure out why their code only runs to a point. Well, we're missing basic steps in the process. We're missing basic variables. So the three tools we just talked about, the IPO table, the flowchart, and the pseudocode are are the three main methods that you'd use to get organized. But in order for each of those to work effectively, in order for the whole process to be intuitive, you have to get away from a bad habit, a really horrible habit that most computer science professionals and unfortunately instructors, when they teach people about coding, they often use single letter variables. Now we're used to single letter variables in algebra, or variables, the elements in chemistry with just one or two letters, right? So we're used to seeing one or two letters for a variable name. The problem is that that's not very descriptive. A variable name ideally should always include a leading hint about the data type. So you might have a whole number, which would be integer. So int could be the way that you start the name for a variable that stores whole numbers, or str for string, if you're storing a string of characters, letters, and symbols. So text, right? Or numbers with decimal points. So real numbers with decimal points. You could use FP for floating point, or RL for real. If you have logical decisions that are made, the true false or the yes no, that's a Boolean data type. So you could use the letters B, O, O. You always want to lead your variable name with a clue about the type of data that's stored in it. And this comes in very handy because sometimes computing applications just don't run because the data type is off. For example, telephone numbers are not numbers that are used in computation. Those are characters that are used along with other demographic information like a street address and telephone numbers and social security numbers. And then dates are a special data type. So you can have numbers that aren't used for calculations with mathematical operations. A lot of times you can have numbers that just represent a person's address or their phone number, and those have to be treated differently. So if you store numbers that are text information, like telephone numbers, and by accident you put it in a variable that's used in a calculation, you'll get an error code. The problem with coding that frustrates most people is that the error codes are kind of cryptic. But when you use decent descriptive variable names, the error codes have much more meaning. They're sensible, and you can quickly resolve a problem. So never forget that you want to include this data type because that's a common problem. You also want to follow the data type with a brief description of its purpose. So 2 or 3 words that describe its purpose. When we say camel case, what we say is that the words that describe that purpose each start with a capital letter. And so as you follow and read along, it's like the humps of a camel every time you hit a capital letter. That's the meaning of the word camel case, right? So a bad example of how you would name a variable is I. Does I mean input in this case? Does it mean integer? Does it mean increase value? What the heck does I mean? We see a lot of X's and A's and I's and so on in computing statements, and the problem is that with all the rest of the functions, if you don't have more information, you can't make any sense out of it. And we'll show you a bad example and a good example in just a minute. So here's a good example. This is whole number, integer, and it represents the current temperature. So I know that we're dealing with whole numbers, int for integer, and I know that what's stored in this variable is the current temperature. So when I'm working with a software that I'm creating that has to do with a temperature probe, this is where I can store the current temperature, right? Now, without these helps, this is the kind of gibberish that happens. You have other functions that you use to build code, but if your variables are one or two letters, by the time you put it uh, in with the rest of the statement, it's really hard to make out what's going on. And this is an actual example of code that I found on a UVI whiteboard when I first arrived in 2016. And this wasn't the College of Science and Math. It was a different course with a different instructor. But this is really hard to follow, and it's hard to figure out, okay, what's really going on here? But if you use the basic changes that we've been sharing with you, and you apply that secret sauce, you take the time to create meaningful variable names, and notice the variable names have no spaces. I want to show you an example of how clean and how sensible the code can be. And so this is actually pseudocode, and we're ready to bring it into a programming environment like Python or like Java. So let's pretend that we're creating some code because we had a thermostat and we had an automatic climate control system with our air conditioner, but it failed and it's damaged. Well, let's pretend that there was a bad storm and that part of it's ruined. And let's also pretend that the air conditioner still works. We just don't have the thermostat. We just don't have the automatic stuff to make it cut on when you get to a certain temperature. What you want to do here is remember the logical condition. It's that stepchild or neglected cousin at the family reunion. We said that the logical conditions are those things that people don't think about first and foremost. But it really helps you frame a quick and easier way uh, to create something useful, right? So I start with if the int current temperature, that's the example we already saw, int current temperature is less than or equal to 76. So I'm measuring 76 degrees, could be Fahrenheit, probably. Celsius would be kind of hot. But if the whole number value for the current temperature is less than or equal to 76, then my AC state equals off. Remember, Boolean states are on or off. So I've created a simple logical condition that I can test for. If it is less than or equal to 76, then that's true. So my AC state, which is a Boolean value, that's a Boolean data type, I'm going to set that to equal off. But otherwise, the AC state is on. So only when the temperature is less than or equal to 76 is my AC unit off. Otherwise, my AC unit is on. So in 3 lines of simple code, I figured out I can use this with a Raspberry Pi, a $35 Raspberry Pi. I can add a $5 temperature probe. Now I can connect that to my AC unit, the power for my AC unit. And lo and behold, I've just figured out how to fix the automatic climate control for my house with 3 simple lines of code. Now I know that's an oversimplification, especially when it comes to like the power control and the temperature probe, but you get the idea here. I can write quick code, simple code, powerful code, effective code that can test for a condition and then take action as needed, right? And that's the revelation we care to capture today. Now, we did say that there was one other matter we wanted to share with you. We said that if you didn't use these methods to create clear, sensible code, really bad things can happen, especially with the logic. So we were going to use algebra to prove that 2 equals 1, and we're going to cheat. We're gonna use single letter variables, and this is just one way of showing you how warped or how dangerous the use of single letter variables are. Once again, I think in part one I shared that uh, not too long ago there was a programming error that Boeing didn't catch, and the supervisors, the quality assurance folks, didn't catch, and the engineers didn't catch, and the final testing phase didn't catch. And then one of their newest airlines crashed, and it killed 200, 300 people every time it crashed, and it didn't just happen once. It happened over and over again, and they had to ground the entire fleet of aircraft until they figured out what was going on, and it was a logic error in a single line of code that was killing hundreds of people at a clip, right? So here we go. Oh, the other thing that's a real benefit is that when there are mistakes in code, if you have sensible variable names, the debug process is much plainer. So let's get back to what happens. So this is called the vagaries of single letter variables. So when things are vague, that means they're fuzzy. We don't know what they're about. All right, so let's go back in time. You're in 8th or ninth grade, maybe 10th grade, whenever you took algebra. And one of the things that we learned in algebra is that if we take a value, a variable on one side, and we have a variable on the other side, so long as we do the same on both sides of the equation, if we want to solve that equation and try to figure out the values of A or B, then we're good, right? So let's give some examples of what we're talking about. If I multiply both sides by A, because I'd like to solve the value for A and B, and I multiply A by A, that's A squared, and if I multiply A by B, I get AB. And according to the laws of algebra, I'm still good. So if I'm trying to solve this algebra equation to determine the values for A and B, as long as I do the same thing on both sides, I'm good. And this should ring a bell for you. Let's keep going. Except when you only have single letter variables with code, it's easy to get lost in the process, right? So what we're going to see here is that something really off starts to happen. We're going to continue the algebra exercise. So we're going to subtract b squared from both sides. So if I take my a squared equals ab and I subtract b squared from both sides, according to the laws of algebra, I haven't changed the equation. The equation is still valid. I can still solve for the values of a and b. And essentially, if I have a squared minus b squared, and then on the other side I have ab minus b squared, this should ring a bell. Oh, I have a squared minus, that's like x squared minus y squared. I can factor, right? So you can factor both terms. So I have a plus b times a minus b, and then b times a minus b. So I can pull the b out of here, and I have a left, and I can pull the b out of here, and I don't have b squared, I have b. So now I have two common elements. If I'm trying to solve the equation, I can cancel both of these on, I can cancel both of these out on both sides. When you have two similar things on either side, if you cancel them out, then you still haven't changed. So let's do that here, right? Let's keep going. We're going to divide both sides by AB. When we're canceling, what we're really doing is dividing by A minus B. See, so that lets us cancel, and then we have A plus B equals B. Well, now right about here we should start to think, not so sure this is right. So up to this point, everything was valid in terms of how we work algebra, but now if I remember that A equals B, I can substitute B for A. We started off with A equals B. So I can take B and substitute it for A, or vice versa. If I have a B, I can substitute for A. In this case, I'm going to substitute this A with a B since they're equal. So what I end up with is B plus B equals B. Uh-oh. So if I combine this and I start to use coefficients, well, B plus B is 2B, and B is actually 1B. We just don't put the 1 there. So if I divide both sides by B, I get 2 equals 1? Oh, what just happened here? I did everything I was supposed to do in algebra, typically, but somewhere along the line there was a mistake. There was a rule broken. And here's what happened. If you go back and we go all the way back, this is the clue. Since A equals B, an expression that right here, if A equals B, then A minus B is equal to, well, if you're subtracting a value from itself, the answer is 0. So if A equals B, an expression like this would basically be equal to 0. So in coding, we have single letter variables or 1 or 2 letter variables. And because they're not descriptive, we start to miss simple, we start to skip over or take shortcuts or miss simple details that can have a huge impact. So if I have 0 here and I'm canceling A minus B on this side and A minus B on this side, what I'm effectively doing when I cancel is dividing by A minus B on both sides. And when I divide by A minus B, we said A equals B to begin with, so that's really 0. I'm dividing by 0. Now, one of the most common mistakes that we afflict on young children is we tell them when they're growing up, division by 0 is impossible. That's a very common statement. Division by 0 is impossible. And mathematicians, professional mathematicians would say, no, that's not accurate. What you really want to say is that division by 0 is undefined. It's not impossible. You can divide by 0. We just did that. We canceled the same value on both sides. But the problem is when we divide by 0, it's undefined, meaning it's a wild card. So the answer that you have can be anything, and it's wrong. The bottom line is that undefined means it's a wild card and you don't have any confidence in the outcome. This is in a similar manner, through the same kind of process, when we do simple coding activities, when we want to create a simple application with basic coding statements, whenever you use single letter variables, you're asking for it. Because you don't know what's the data type. You don't know what the purpose of the thing is. And then when you're building out the statements, you're not going to see, oh, wait a minute now, that's false. Oh, wait a minute now, that's 0. I can't divide by 0. You miss things. And then planes crash and hundreds of people die. That's the reality of the world we live in. So if you want to create logical, reliable, accurate data, we don't want to spitball when it comes to the accuracy of code that predicts where hurricanes will go. We don't want undefined code when we're creating software to simulate where the hurricane's going to turn. We want the most accurate statements. We want our code to be consistent in terms of the results it renders. So in a very simple way, we never want to use single letter variables. And I hope that this short walkthrough was something to pique your curiosity and kind of tickle the thoughts that are rattling around. And the rest of coding is actually pretty simple. So coding in a specific language flows directly from the pseudocode. We said if you have good pseudocode, when you start to work with the actual statements in a programming environment, the statements write themselves. Now, the other thing that you want to do all the time is create a prototype using something like Python. Because pseudocode is written in English, many Python statements are, are, are very much like English. So you build the prototype in Python, you make the leap from pseudocode to Python code, which is actual programming code. And because it's an interpreted language, it's going to give you a prototype that works, but it's not tweaked for performance, right? If you get the prototype working, then you can go back, use the same pseudocode, and instead of working with Python as a programming language, you can use a programming language like C or C++ or Java, right? So Python is ideal for prototypes. You always want to build prototypes to see if things are working right. And then if there's a lot of computing, if there's a performance issue for that code, you want to rewrite it and compile it for production use. The last thing we want to leave you with today in the second part of our session is this simple graphic that I drew by hand. So we talked about IPO table, the inputs, the process, and the output. And there's a similar thought that follows for each. There's a similar component of scientific computing that's related to each. Related but not the same. So, and we'll explain more as the course goes on. So inputs is about data collection, and that's part of scientific computing. And process is about analysis. That's the engine in your car that makes this thing go, right? And then the output, that has to do with the patterns. So when the data is analyzed properly, what you get is output where you can identify patterns, pattern recognition. So the goal of scientific computing is to take raw inputs in terms of digital information, that data, and then to process it so that the outputs provide patterns we can recognize. Oh, this is increasing. Oh, the relationship of this has to be squared or inverted. The important thing to remember is that the whole purpose and reason we're working with outputs is to build our capacity to read the tea leaves, to predict. And that's really what the coding process is about. It's a scientific tool that helps us understand the data and predict what comes next. We're going to take a look in our next class at Excel, and I want you to notice something real obvious here. I've misspelled Excel, and that's because we're going to be focusing on the cell. That's one of those components of an Excel spreadsheet, and that's the very reason why I've done this here. So I want this to stick in your brain like something that's odd, and we're going to show you how to automate calculations and calculating a series of data points in Excel. But Excel itself is an excellent primer about the coding process because every cell in Excel can store inputs. It can be used to process or analyze, or it can be used to display output. We'll share more in the next session. Thanks for joining us.